has a unique maximum. So we want to show that m zeta is maximized as zeta null, and then next we'll show the uniqueness. So first you can see that this one is actually Kullback-Leibler minus of the Kullback-Leibler function, right? And so because we already studied that Kullback-Leibler function is always non-negative, so minus of the Kullback-Leibler function is non-positive. With equality if and only if, right? That is the property of the Kullback-Leibler inequality. So next, m zeta null. If you plug in zeta null here, then this one is 1, right? So then log 1 is 0. So that's why we have 0. So combining these two, we can see that m zeta has a maximum at zeta null. And now to show uniqueness, we suppose that we have another zeta 1 which satisfies this. Then the definition, right? What is the definition of the meaning of, okay, sorry, meaning of this guy? Well, that is minus Kullback-Leibler of zeta 0 and zeta 1, right? So this one, if this is 0, that means what? That means this density are equal, right, with the property 1. So then on the identifiable implies, so identifiability condition implies this. So that means zeta 1 is equal to zeta 0. That means we have a unique maximum. So lemma 1 simply says that on the identifiability, this guy. So you can see m zeta. What is m zeta, by the way? Is m zeta log fx zeta, right? That's zeta minus zeta log fx zeta 0. But this guy, the second term, is actually constant. Right? So that means maximizing m is equivalent to maximizing the first term, which is expected value of the log function, log density. So we can, if we consider, okay, and now if you consider this q function, so qn zeta is essentially 1 over n times log. So this is log likelihood, right? Likelihood function. So constant times, so 1 over n is just to make it like a sample mean. So log likelihood function. And so a maximizer, MLE is the maximizer of this q and zeta by definition. And then you can see that this is a sample mean, right? Sample mean of log fx zeta. So this is another, it's like you can think this is another random variable, then it's just the sample mean of the y's. So you can see that this one will converge to its mean, right, which is q. So it's q zeta null, and then also we'll have this one. And then you can see that this guy, by the way, the limit term, this guy is positive by because we just said that so this one is actually what, m zeta 0 minus m zeta, which is, that's what we just saw, right? We already the previous lemma, just to show that this guy, okay, so this guy is positive because this is m zeta null minus m zeta. So we can establish, so that means q and zeta null will be larger than q and zeta with priority, right? So this priority, this event will be more, this will have a priority converge to 1. So that is this problem. That is this this result. Okay. So that is this theorem. So the log-like function has a maximum as zeta null with high priority, increasing to 1. So if you, but by the definition of MLE, Ln zeta is the MLE, right? MLE is maximized. So it's like this. You can, so this is Ln, okay? This is Ln zeta, and you, so it's a function of n. So if you, and then this one is zeta hat, right? And then because it's maximized, but in the limit, so the limit of this Ln, the limit converges to maybe, right? So this is the limit. This is, so this is kind of that is here we use the Q, right? That is, this is Q. So the Q zeta will have a maximum zeta null, right? But the message here is that this theorem says that even though finite, so what is this value? So this value is actually Ln zeta null, right? So Ln zeta null. So this one. So this one, Ln zeta null, may not be the maximum, right? So there's actually may not be the maximum, but the message is that if you have a large sample, if you increase sample size, then this will move, right? Move to something like this. So then the Ln will go up, because if you because as n increases, then so basically it will converge to Q zeta, right? And which is the maximum. So basically this maximizer, right? This zeta hat n will move to zeta 0, right? I don't know how large you can see, but that is the kind of explanation. So basically, if this Ln converges to Q, then this value, right? This value will converge. So L zeta null, this will converge to Q null, right? And then the original maximizer zeta hat n will converge to zeta null intuitively, but we still need to prove it. So under some additional assumptions, we might expect this one. And so here's the formal theorem, and the theorem is that we have an interior point, okay, interior point, and then differentiable and solution to unique. So we it's kind of stronger than necessary, but this make life easy. So you can. So what is this? What is the meaning? Okay. So let's consider zeta minus epsilon, zeta 0 minus epsilon, zeta plus epsilon. Okay. Then what? Then and then L. Okay. Ln zeta null is a little bit. So this is a log like L, and zeta null. So think of this event, okay, and Ln zeta null log likelihood. It's not log likelihood. This guy. Zeta null plus epsilon. So if you consider this set, so let's use this assumption graph. Okay. So this is L. So you don't have to. Right, the assumption, this is likelihood function, and the likelihood function has a unique maximum. So and then so the maximizer is not necessarily equal to zeta null. So let's say that zeta null is here. Okay, and zeta hat is here, right? And zeta null plus minus epsilon. So if you, okay, so say that this one is zeta null minus epsilon and zeta plus epsilon. So what we care is that if this is true, so if this is true, okay, right, this one, so the first event is zeta, right? This is L and zeta. So the log-like function at zeta null is higher than zeta minus epsilon, right? And also zeta plus epsilon. So if you view that this one is always is greater than, as long as you choose epsilon or c large enough. So this is you don't have to, let's write a c to avoid confusion. Okay, so as long as you make c to guarantee that this property holds, then the maximizer zeta hat will be with a smaller, same c. So because why? Because we have a unique maximizer. So the unique maximizer supposed to be cannot be outside this region, right? So this is the range, and the maximizer cannot locate outside because of this one. Okay, so that means this probability will be less than this probability, and this probability is converges to 1, so this probability will converge to 1.